So welcome back. Now we're in the activity 2 of scaling. So as you may know, we're using the import nump as MP, the import cv2, and the import matplotlib payload as plt. So first of all, we have this image equal to cv2.imread. This is the location of our image. This is the same one as always, the one. Then we have the inputs equal to cv2 point cbt color. So we have image and cv2 point color bgr2 rgb. Then we have rows, calls, and channel equal to image point shape. Then we have t equal to mp float 32. So the ranges are 1, 0, and minus 50. Then we have 0, 1, and 50. Then we have the output of the CV2 warp up flying. So we have input T calls rows. So columns and rows. Then we have the PLT show output and the PLT title shift image. So this is gonna be displaying the image, and in the borders it will be displaying the dimensions of the image. So in the right is gonna be the some scaling scaling float numbers, and in the row in the bottom of the image it will be displaying also scaling information. So I'm gonna run the program so you have a better understanding of what I'm explaining right now. Uh, there you go. This is the shift image. So we have here the scaling in the left and scaling on the bottom. So see you in the next one. Hello, so now we are in the next activity of scaling. We are in the third activity. This is about rotation. So we are using the import cv2, the import matplotlib pyplot as plt. Then we have the image equal to cv2 read. This is the location of our image. Then we have the input equal to cv2.cbt color image cv2.color bgr2 rgb. Then we have rows, columns, and channel equal to image point shape. Then we have the r equal to cv2.get rotation matrix, and then we have calls divided by 2, rows divided by 2, and then we have 45, and then we have 0.5. Then we have the output equal to cv2 warp pa fine. Then we have the input r, calls, and rows. And finally, we have all the same as I was. We have the PLTM show output, the PLT title. This is the rotation and downscale image. This is the title that will be displaying when I run the program. And we have finally the PLT show. So this accepts the angle of anti-clockwise rotation in degrees, the center of the rotation, and the scaling factor as arguments. Then it creates a matrix of the rotation operation that can be passed as an argument to the call cv2 warp of a fine function. The following example applies to the rotation operation to an input image within 45 degrees as the angle of the rotation, and the center of the image as the center of the rotation operation. And also it scales the output image down to half, 50% the size of the original input image. So I'm gonna run the program so you can have a better look of the code. Run module. Let's wait a second. There you go. We have here the image, as you can see, is rotated, and also is the 50% of the scaling. So we are using two techniques in this program. Hope you learned something, and see you in the next one. Hello, welcome back. Now we're in the animation and rotation. So we're importing the CV2 from time import and slip. So first we charge the image. So we implement the image equal to cv2.imread. This is the location of our image. Then we get the dimension of the image with rows, calls, and channels equal to image shape. then we have the angle equal to 0, and we have a while true. So while true, if angle is equal to 360, angle equal to 0. Then we have the matrix rotation. So M is equal to CV2 point get rotation of the matrix, and then we have calls divided by 2, rows divided by 2, and angle 1. So then we have rotation equal to CV2 point warp affine image M calls and rows. Then we have show image rotated, and we have CV2 point show rotation image rotated. Then we have angle plus equal 1 sleep 0.02. I mean, then we have a button ask to finish the operation with the CV2 point wait key 1 equal to 27. Then we have break, and finally we have close all the windows with CV2 destroy all windows. So we can also create a very nice animation by modifying the preceding program. The trick here is that in the while loop, we must change the angle for rotation at a regular interval and show those frames successfully to create the rotation effect on a still image. The following code is an example or a demonstration of this. So I'm gonna run the program so you have a better look of what's happening here. So as you can see in a sec, the image is rotating 360 degrees. So it's rotating the angle of the image by a second. So if I wait a bit, you can see that it will be upside down. So let's wait a bit. Almost. There you go. So as you can see, it's upside down, and then it will be. So here we have a trick for the webcam. As you can see, we have a new code. In this case, we are using the same concept of the last clip. We are rotating the image, but in this case, the image will be the webcam. So it will be rotating a video in live action. So first of all, we have the import CV2. Then we have the from time input sleep. Then we have the cap equal to CV2 video capture. And then we have the read, the frame equal to cap read. Then we have rows, calls, and channels equal to frame point shape. Then we have an angle of 0. Then we have a while, and in this while we have red frame equals to cap point red, if angle equal 360, angle equal to 0. Then we have the M equal to CV2 get rotation matrix, calls divided by 2, rows divided by 2, angles 1. Rotation equal to CV2 point warp affine frame M, calls and rows. CV2 arm show, and this is the name of the rotation image, rotated. Then we have angle equal to angle plus 1, sleep 0.2, if CV2 point wait key 1 equal 27. This means that if I press the ESC, it will interrupt the run. Then we have CV2 destroy all windows to end the program. So I'm gonna run the program so you have a better look of what is going to be happening with the webcam. So I have here the webcam. I'm gonna show you in the image. So I have here the webcam, and I'm gonna put this down, and I'm not touching anything, and the image is rotating, as you can see. The video, I mean. See you in the next one. Now we're in the next activity. This is a affine transformation. So, first of all, a affine transformation is a geometric mathematical transformation that ensures that the parallel lines in the original input image remain parallel in the output image. Now, The usual inputs to the affine transformation operation are set of 3 points that are not in the same line in the input image and the corresponding set of the 3 points that are not in the same line in the output image. So, first of all, we have these two imports, CV2 and nump as MP. Then we have the from matplotlib import pyplot as PLT. Then we have the load the image. So we have image equal to cv2.mread, and is the location of my image and the name of my image. Then we have the conversion of the image to BGR to RGB using the input equal to cv2.cv2 color image cv2 color BGR to RGB. Then we have the get the dimension of the image, rows, columns, and channels equal to input shape. Then we have the defined points for the affine transformation. Points 1, the MP float 32, 100, 100. Then we have 300, 100, and then we have 100, 300. Then the points of points 2, MP float 32, 200, 150, 400, 150, 100, and 300. Then we have the calculate of the affine transformation of the matrix. A equal to CV2 get affine transformation from points 1 and points 2. Then we have the apply the affine transformation. Output equal to CV2 warp affine input A calls and rows. Then we have the display of the inputs and output images. PLT subplot 1 to 1, PLT show input, PLT title input, PLT subplot 1 to 2, PLT show output, PLT title affine output, and then we have the show the plots, PLT show. So now I'm gonna run the program so you have a better look of what we are doing here. Let's wait a bit and you will see the two images, the two figures. We have the first one, the input, the original one, with the scale factors in the right and the below part. Then we have the affine output with the in the left part with the scales. And so now we're in the next activity. This is about perspective transformation. As always, we are using these two imports, the CV2 and the nump as MP. Then we have the from matplotlib import pyplot as PLT. Then we have the image. So we are using this location, my location, and the image is called 1. Then we have the conversion of BGR to RGB. So we have the input equal to CV2 color image CV2 point color BGR to RGB. Then we have the obtain dimensions of the image. So we have rows, calls, channel equal to input shape. Then we have the points of the transformation of the perspective. So points of the S1, we have the float 32, 0, 0, 400, 0, 0, 400, 400, 400. And then we have the points 2, MP, float 32, 0, 0, 300, 0, 0, 300, 300, 300. Then we have the calculation of the matrix of the transformation of the perspective. We have P equal to CV2 get perspective transformation points 0, 1 and points S2. Then we have the application transform of the perspective. Output equal to CV2 warp perspective input P 300 300. Then we have the show images of the input and the output. We have the PLT subplot 1 to 1, PLT show input, PLT title input image, PLT subplot 1 to 2, PLT show output, PLT title perspective transformation, and show the graphics PLT show. So as you remember, it's very similar to the last code, but we have a different kind of design or dimensions in the second image. So I'm gonna run the program so you can get a better comprehension of what we are doing here. So this is the image and this is the perspective transformation. So that's all. See you in the next one. Hello, now we're in the next activity. This is stress holding images. So as you remember, we are using the same imports, so we are using the CV2, the matplotlib pilot as PLT, and the nump as MP. Then we have the import image, so we are importing the image that we have in our computer. I'm using the same image as the first activity of this chapter. We are using the 1, it's a wolf. Then we have the th equal to 127. Then we have the max value equal to 255. Then we have the red 01 equal to CV2 threshold, image, th, and max value, CV2 point trash, binary. Then we have the print 01, we have the red 02, the red 03, the red 04, and the red 05. Then we have the titles, input image, binary, binary invert, T0, T0 invert, and TRUNC. Then we have the output image 01, 02, 03, 04, 05, and then a 4 I in range 6 PLT subplot 2 3 I plus 1 PLT I'm show output 1 C map grade, then PLT title titles I, PLT axis off, and PLT show. So when I run the program, you will see a lot of images from different thresholdings. So you will see different styles. So I'm gonna run the program. Mm. Um, so we have here the images. So we have the first one is input image, the basic one, the one that we have in our computers. Then we have the binary, and then we have the binary invert. Then we have the TO0, the TO0 invert, and the TRUNC. So this is all the thresholding of the image, and see you in the next one. Now we're in the final activity of this chapter, chapter 6 of the activity 4. So this is about adaptive thresholding. So in this code, you will see in the output 3 images. The first one, the original, and the second and the third one with a specific style. So first of all, we have the 2 imports, the CV2 matplotlib pilot as PLT. Then we have the import the image. So we are importing the image of this location, is the same as always. Then we have the conversion of the image to different gray scalings. So we have the gray image equal to CV2 CVT color image CV2 color BGR to gray. So it's transforming the image to gray. Then we have the defined parameters of the umbral adaptative to block size 1 to 3 and the constants to 6. Then we have the apply umbralization adaptative with a method in media. So we have the threshold in 1 to CV2 adapted with threshold to gray images 255. CV2 adaptive threshold mean C, CV2 threshold binary, and block size constant. Then we have the application of the relation adaptative with method using. So we have the threshold in 2 equal to CV2 adaptative threshold gray image 255, CV2 adaptative threshold using C, and CV2 threshold binary block size constant. Then we have show the image original and the results. So the output will be the gray image threshold 1 and 2, and the titles will be original, so it's the original image. Then we have the mean adaptative and the using adaptive. So you will see the 2 styles in comparison with the original style, and then finally we have the show images. So we are using 4 I in range of 3. We have the PLT subplot 1 3 I plus 1, PLT and show output I, CMap gray, PLT title titles I, PLT X ticks, and PLT Y ticks. Finally, we have the PLT show to show the result. So I'm gonna roll the program so you have a better look of the 3 images, the original, the mean adaptive, and the Gaussian adaptive. So as you can see, we have the three images, as I mentioned earlier, the original, the mean adaptive, and the vision. Hello, welcome back. Now we are in the activity 4, chapter 6. So this is the first activity of the chapter 6. This is about color spaces. So color spaces is a mathematical model that is used to represent a set of colors with color spaces. So we can represent colors with numbers. Let's look at the first way. So we are implemented three merges, the R, G, and B. So as you can see, we are importing the CV2, the matplotlib. So first we are equaling image with CV2.imread. This is the location of my GPG. So the name of this is 1. And the name of the title is color image. So I'm gonna run the format so you can see how it's working. Let's see. Oh, there's a mistake. Let me run again. And let's wait a second. There you go. So this is the image. So see you in the next activity. Hello, welcome back. Now we're in the activity 4, chapter 6. This is the second activity of this chapter. This is about color spaces again. This is another way to implement the RGB in an image. So let's check it out. I'm gonna run the program. We can use the cv2.cvtcolor function to change the color space of an image from BGR to RGB as demonstrated in the following code. So let's check the code. So this is the location of our image. It's the same one as the last clip. So as you can see, the name is 1 of the wolf. So the title then again is color image, and it's pretty much the same as you can see. So see you in the next activity. Hello. We are in the activity 3 of color spaces. So we are in the activity 4 of chapter 6, color spaces. So in the preceding code, we use the CV2 color, the RGB flag to color conversion. The OpenCV has plenty of such flags to color conversion. We can run the following program to see the entire list. So I'm gonna run the program so you can see what is happening here. Run model. So as you can see, this is all the model of the colors. So there are 346 color space conversion flags in the OpenCV 460. So let's jump to the next activity. So now we're in the activity 4 of color spaces. So we are using the HSB for color spaces. The term of this HSB stands for hue, saturation, and volume. In this color space or color model, a color is represented by the hue, also known as the tint, the shade, which is the saturation scale of the amount of gray and white and black on the extreme ends, and the brightness, the value of the luminescence. The intensities of the color red, yellow, green, cyan, blue, magenta are represented by hue. In terms of saturation, means the amount of gray component present in the color. The brightness of the intensity of the color is represented by the value component. So the following code converts a color from the RGB into the HSB and prints it. So you can see we have these codes. This is my location of my picture. So then again, I'm using the same image, the wolf. That's the name is 1. we are using, as always, the import CV2, and as you can see, we are using the HSV. So we are using the RGB hue, saturation, and shading, and also the white, black, and gray. So I'm gonna run the program so you can have a better look of what we are doing here. So let's check it out. So let's wait a second, and mm, so all over here. There you go. So here's the saturation demo of the picture. So see you in the next one. Welcome back. So now we're in the next activity. So as you can see, we are using tracking. So this is the first activity using tracking. Tracking in real time based on color. So now let's learn how to demonstrate the concept of converting color space to implement a real life mini project. So we are using the HSV. We are now familiar with this concept because in the last activity we used it. So as you can remember, we are using the hue, saturation, volume as in color space. So make it easy to us to work with range of color to track an object that can have colors in a specific range. We need to convert images, color spaces into the HSV and check if any part of the image falls within the specific range of the color we are interested in. So as you remember, is the OpenCV and has the function of the OpenCV and also the CV2 point in range. So that offers the functionality to define a color range. So I'm gonna run the program so you can see what is happening in this new program of tracking to track the value of the HSV. So there you go. The tracking is looking for a specific color. So there you go. As you can see, I have a candy in there that is green, and in the output is also green. So it's the only color that is represented on the output. So as you can see, the first image is ignoring all the colors of the HSV, and the only color that's gonna be displayed on the output is the green. So you can set any color you want. In this case, it's the green. So see you in the next one. So now we are in the activity 2 of tracking. So this is tracking in real time based on color. This mask is purely black and white. As you may know, we are using binary image. If we make modifications to the preceding code, we can track objects that have distinct colors. So we must create another mask of the range of colors we are interested in. Run this code and check for yourself your output. We can also add a track bar to this code to select a range of blue or green colors. So we are using the import nump as np, the import cv2, and def empty function. So we have cap equals to cv2 video capture 0, window name, so this is the name that will be displaying in the output that says object tracker. Then we have the track bar name, and the name is color chooser. Then we have the cv2 name window and the cv2 create dashboard. Then we have an while and else. So in the while true, we have this block of code, and else we have that block of code over here. So you can copy and make sure that you have the same output. And then we have the break and the cv2 display all windows and the cap release. So I'm gonna run the program. So this is the object tracker. So it's tracking a specific color. As you can see, in this case it's a green. So I have a candy over there, and it's displaying the color of the green. And also I have a program over here that is displaying the green. So see you in the next one. Hello, so now we are in the next activity. This is about scaling. So I have already run the program, so you can see what is happening with this code. We have in the left the downscale. This is the first image, and now we have the upscale of the same image. The image I'm using is the same as always, is the number 1. It's located in that part, so you have to make sure where is your location of your file. I have in this place. It's located in this place, and this is the name. I name it like 1. So now let's see what is scaling. So scaling means resizing an image. It is a geometric operation. So OpenCV offers a function, the CV2 resize. For performing this operation, it accepts an image, a method for interpolation of pixels, and the scaling factor as an argument, and returns an scale image. So the following methods are used for the interpolation of the pixels in the output. And so that's all. See you in the next one.